So now I want to come to Lorentz transformations. Okay. So what are Lorentz transformations? So Lorentz transformations are transformations that leave delta S squared invariant. Okay. So let's put some mathematics to it. Without loss of generality, let x1 of mu be the origin and x2 of mu be just x of mu, right? Then delta of S squared becomes x mu, x nu, eta mu nu. What is eta mu nu? Eta mu nu is a 2 by 2 matrix. It's actually a tensor, but here we are. Okay. So if I write this out explicitly, then I'm going to have, this is basically, see that only the 0, 0 and the 1, 1 component is non-zero. So I will get x0, sorry, we'll get minus x0 squared plus x1 squared. Okay, so which is minus t squared plus x squared. Okay. So the Lorentz transformation is something that leaves this quantity invariant. Okay, how do we do this? So suppose we have a point, space-time point, an event, and I apply Lorentz transformation, a linear transformation. So I get x prime of mu. X prime of mu is related to the old one by a matrix acting on the old one. Lambda is a matrix, 2 by 2 matrix. Okay. Then according to special relativity, this thing is invariant. So this is equal to x mu, x nu, eta mu nu, but it is also equal to x prime of mu, x prime of mu, eta mu nu, right? Is this clear?
Because it kept the interval invariant.
Yeah, exactly, by definition. So, but what does it imply for this matrix? That's what we want to know, right? So let's write this line first on the left. And then this thing, which is x prime of mu, x prime of mu, eta mu nu. But this thing is lambda mu sigma, x of sigma. And this thing is lambda mu rho, x of rho, eta mu nu, where we are employing the Einstein convention. So anytime an index is repeated, there is an implicit sum. So is it clear what I did coming from here to here? I just used this definition. This, the fact that we are making a Lorentz transformation. Okay, so I'm just going to wait here to see if there are any questions.
Sir, the way you wrote the the expression for S square having the eta matrix on the right hand side. So will there be like a superscript or subscript like index, because like otherwise how would you deal with the cross terms that might appear? Like the cross terms of tx or t prime x prime or things like that, because probably we don't want them here.
Well, this is diagonal, so there is no cross term here. I mean, if there were a cross term, I wouldn't have a problem.
Okay.
I mean, why would I, what's the problem with this notation? It's summed over both of these indices.
Yeah, I mean, I was saying that the right hand side is a matrix if we consider each of those as a number. If
This
not,
is a matrix, this is a column matrix, this is a row matrix, so the whole thing is a number.
okay. Yeah.
Right? Well, what you're saying is that I can write.
Oh, I know what I was confusing. I probably saw the notation like downwards and upwards, so I was confusing it with it.
Yeah, this is how I've written. This is the matrix notation, but here I'm writing it in terms of indices. Okay, so coming, this way means that if this is going to be true, then this means that, let me just write this. Let me cross it out. This is lambda mu sigma lambda nu rho. তারপরে এখানে হবে হচ্ছে গিয়ে yeah, so eta mu nu x sigma x rho. Now on the left side here, instead of mu nu, let me just write this as eta rho sigma, and here, because these are dumb indices, right? I'm summing over them, so it doesn't matter if I'm using mu nu or rho sigma, right? So these x's are arbitrary, right? So this equation to be true must be that this equation must be that eta rho sigma must be equal to lambda mu sigma lambda nu rho eta mu nu. So the lambda matrices must satisfy this condition for the interval to remain invariant. Sorry, I'm making things worse. Okay, so if I want to express this as a matrix, let me introduce the matrix eta. Then this is, if you look at this is row column row column row column. So I have this guy, this guy, this guy, but you see that this row is being contracted with the row here. That means I have to put a transpose here, right? So this is the condition that the Lorentz transformations have to satisfy. This is analogous to the SO2 matrices that we saw, where here we, instead of this eta matrix, we had an identity matrix. So this was basically O2. Okay, how's it think? This was the definition of O2. And this is the definition then of O. This is called O1, 1. Okay. So these are orthogonal matrices. What happened here was that this was the Euclidean metric, the Euclidean metric, and here, instead of the Euclidean metric, we have the Minkowski metric. Okay. So this is the O1, 1. This is known as the Lorentz group. Okay, this is the abstract definition of the Lorentz group. Are there any questions?
Could you go a little bit up?
Yeah.
Yeah, so the line before that, like how did you arrive at the line before that? I mean, this one.
Okay, so here what I'm saying is that for this to be equal to this for arbitrary x's, this has to be equal to this thing, right?
Oh no, my question was like the line before that from this expression, the last line.
This
So
one?
yeah, from this one to the next one. So
I
like
mean, these are all matrix elements, right? There's some, but there's a matrix element. So I can move things around, right?
oh okay, yeah.
These are all matrix elements. As long as I'm keeping all the indices the same, it doesn't matter which, and these are not quantum operators. So, okay, any more questions?
I have a question actually.
Yeah.
So is like this looks like some sort of conjugation by lambda. Is this some kind of rotation as well?
Yeah, it's a generalized rotation.
I see.
Because, in rotation, what's kept invariant is the Euclidean norm, right? But here, this is the Minkowski norm because there's a minus sign here. So it's a generalized form of rotation. And we'll write down the matrices more explicitly, and you'll see that it is a generalization of rotation. Okay, so this can be, yeah, it's a kind of rotation, but it's not rotation in the usual sense. It doesn't keep the Euclidean norm. It doesn't keep the Euclidean norm invariant. It keeps the Minkowski norm invariant. Which means that, time dilation and, length contraction, all of those comes about from this fact. So it's a very powerful and a very elegant way of expressing the Lorentz transformation. Everything you want to derive about Lorentz transformation can be derived from this one equation. Okay, this is a geometric way of looking at Lorentz transformation. Okay, any more questions before we go on our leave? On our break? Okay, I think it's a good time to pause, and we'll meet back here at 6:15, okay? Okay, so let's start. Right. So we already talked about the conventional parameterization of O 1, 1. So we're talking about O 1, 1, which is the Lorentz group. Now, as in the rotation group, the connected component that is the component connected to the identity is the SO1, 1, which is the Lorentz group, Lorentz transformation that we usually understand. And we saw that these transformations have the form of a linear transformation of this form. Okay, so we can write this as x prime of mu acting is equal to lambda mu x of nu. Now the determinant of lambda, as you can see, is gamma squared minus gamma squared beta squared, right? So which means gamma squared 1 minus beta squared. But this is nothing but the 1 over beta squared. So this is 1. So indeed that we have these Lorentz transformation as we understand them do belong to SO1, 1. So there are transformations such as parity, which are going to be part of. So for example, this is time reversal. So this should be called T. This is time reversal. So what this does is that it takes a future pointing vector to a past pointing vector and vice versa. And there's parity, which reflects any vector in the x direction to minus x direction. Okay, so these are the ones which do not belong to this guy. Okay, which are part of the O1, 1. Okay, now that we have seen the this is the traditional parameterization of the Lorentz group, but there's a nicer parameterization which our Lorentz group. So we know that beta, the speed, the velocity, goes from -1 to +1, right? Because our speed of light is 1, so it can be at most, the speed of our reference frame can never reach the speed of light. Now, if I define a new coordinate, say gamma, psi, which is defined by tan hyperbolic of psi, then this is a monotonic transformation. So psi is a monotonic function of beta, right? Do you understand what this means, monotonic?
Strictly increasing.
Exactly. So if one increases, the other one increases. If one decreases, the other one decreases. Okay. So that means that it's a good function. It's a good map. It's a one-to-one map. Okay. So if I use this, then what happens is gamma gets, sorry, this is not what I want to use. Gamma gets mapped to cosh of psi, and gamma of beta gets mapped to sinh of psi. And then, the determinant of this is automatically 1 because we get cosh squared psi, zeta. This is zeta of psi. Cosh squared zeta minus sinh squared zeta, which is 1. And now if I express my Lorentz transformation matrix in terms of zeta, I get this form, which is very similar to the form we had for the SO2 matrices, right? So essentially, if I take a SO2 matrix, say R of theta, which is say cosine of theta minus sine of theta, sine of theta, and then cosine of theta, then this, you can see that there's a very clear analogy between these two things. Okay. Okay, so this parameter psi is called rapidity. And this rapidity has a clear advantage over beta. And what is the advantage? Suppose I make a Lorentz transformation, and then I make another Lorentz transformation. Then if I look at the resulting Lorentz transformations, I'll have some cosh of zeta, cosh of zeta, sinh of zeta. The minus here is kind of, you can absorb it, right? Because you can always define zeta to be minus zeta. So this is 1, 1, 1, 1. And here we have minus sinh of zeta 2, cosh of zeta 2, sinh of zeta 2, cosh of zeta 2. And using the hyperbolic cosine and hyperbolic sine identities, you can write it as cosh of zeta 1 plus zeta 2 minus sinh of zeta 1 plus zeta 2 minus sinh of zeta 1 plus zeta 2 cosh of zeta 1 plus zeta 2. Okay, so we see that expressing Lorentz transformation in terms of, zeta, that is rapidity, makes the velocity addition formula much simpler, right? Because that velocity additional formula of special relativity, right? It's kind of a hard to kind of memorize. It's not a linear formula, so it makes it a lot more cumbersome. Whereas in case of rapidity, if you have a reference frame which has rapidity, say zeta 1, and you have another reference frame on top of that which has rapidity zeta 2, then the combined rapidity is just addition, right? And we see that rapidity takes value between minus infinity to plus infinity. And this also shows that SO1, 1 is isomorphic to R1. Okay. Any questions?
Sir, do we write SO1, 1 to emphasize that it's not the rotation in like two dimensions, but rather we're working on space-time?
Yeah. So this comma, this corresponds to the signature of your space-time, signature of the metric. Okay. In fact, this guy acts on Minkowski space, and Minkowski space has a measure which is different from Euclidean space. So you will often see R2 written for Euclidean, two-dimensional space. And you will also see quite often written R1, 1 for Minkowski, for two-dimensional Minkowski space, okay?
So they just have the different topologies.
They don't have different, yeah, they have different topology. They have different metric. Yeah. Would you say they have different topology, or
basically we go to the topology from the matrix, so probably they essentially would mean the same thing.
Sorry, did you say we go to the topology from the metric? I thought it was the other way around.
Like we can define an open set in terms of radiuses and distances, so in that sense.
Oh, I see. Okay, right. Anyway, I'm not a mathematician, so I'm not exactly sure. I would say that these have different metrics defined on them. But I see what you mean, yeah.